Seong Jin Kim from National Tsinghua University. So he is going to tell us about high redshift galaxies from Cosmos-Web field. Yeah. Let's welcome him.
Hi, good afternoon everyone. Thank you so much for having me here today. My name is Seong Jin Kim from National Tsinghua University. And today I'm going to talk about our recent work and ongoing project, searching for high redshift galaxies in the Cosmos-Web field. And this is about near-infrared dropout galaxies based on the JWST NIRCam filters. And this work was done with my collaborators, the cosmology group members, and data reduction team. So the questions about how galaxies have evolved and how they have formed the stars. These kind of questions have been one of the hottest issues in modern astronomy and cosmology. So how to understand and how to explain the cosmic star formation history, this is one of the most important and interesting questions. So this figure shows the kind of simplified history of the universe. So we know this kind of model plots, which tells us that the star formation history of the universe peaked around redshift 2 and then decreased afterwards. So this kind of model plot first introduced in late 1990s using Hubble Space Telescope, and then it was improved and refined using infrared data from the Spitzer and Herschel Space Telescope. So recently, when we looked at the much wider range of redshift, we can see that in the higher redshift, so beyond this peak towards the reionization era, the uncertainty is getting larger, as many different work shows different star formation efficiencies. Especially the recent work shows much lower star formation rate density compared to the model et al. 2014. So as we move to the higher redshift, so this kind of questions naturally becomes like this: when the first galaxies were formed, and how these kind of things happen in the early universe. So this is even more interesting questions and important to understand the formation of first generation of galaxies and their evolution, as well as the star formation history of the early universe. So in terms of this kind of model plot, actually we want to know where we can put our measurement in this high redshift. So to find any better answer to these kind of questions, we need to observe the distant galaxies in the early universe. But our current observations have been mostly relying on the optical bands, which are strongly affected by dust obscuration. So to overcome this kind of difficulties, we need infrared observations and infrared data. So we are using JWST. So JWST is the most advanced telescope ever, which is optimized for infrared observations. So this is the powerful window to the early universe. It's 3 times larger than Hubble Space Telescope, and compared to the previous infrared space telescope, Spitzer is 8 times larger. So looking at this, compared to the Spitzer images, we can clearly see that how much the data has been improved. And on the right panel, look at the position indicated by the green arrows. You can see that JWST is much better, and then it's free from the dust extinction. So this is why we are using JWST. And actually, JWST has brought us revolution for high redshift galaxy studies. So for example, so GNG11 is kind of a record by Hubble Space Telescope, and it's spectroscopically confirmed. And the JWST increased the high redshift number of samples, and even higher than redshift 13. For about redshift 8 and 9, the massive galaxies reaching or even higher than 10 to the 10 solar masses have been found and reported. So recently, the galaxies at the redshift higher than 410 are spectroscopically confirmed. This is really interesting. So, probably this must be one of the first generation galaxies. So we need more samples to understand the high redshift galaxies and early universe. So we need to keep searching. So we use the JWST COSMOS data, and this survey covers a continuous 0.5 scale degrees and using 4 near-Can filter bands. And this area is much larger compared to the early released data, survey data. So compared to this other survey fields, the Cosmos covers, this field is more than 100 times larger. So we hope we can find more high redshift galaxies, but the survey provides a little shallower depth. So by observing this kind of large area, we can obtain sufficiently larger number of bright galaxies. So as a result, the uncertainties in the bright end of the luminosity function can be significantly reduced. So we hope we can obtain more reliable data points, reliable measurements. So how we can obtain this kind of high redshift galaxies? So we try to find these galaxies having Riemann break features like this. So in this work, we focused on 1.5 micron dropout. So this Riemann break at 16 angstrom. So at higher redshift higher than 11.5, this break moved to the wavelengths longer than 1.5. So reliable detection, for example, 5 sigma detection at 277 bands and no detection at 1.5 bands, this is what we want. So the criteria, the selection method can be described and summarized using this kind of color flow diagram. So the color criteria was explained by these 3 lines, and these are explained in Harikane et al. 2023. So these 3 lines are described by these 3 equations. And the candidate sources has to be located in this area. But sometimes some sources on the unexpectedly bad sources can be come into this area. So no detection at 1.5 and reliable detection at 2.7. In addition to this criteria, we excluded the sources that matches to the shorter wavelength spans, because we can be sure that this is not kind of dropout sources. And also we excluded stellar sources based on the Weaver et al. 2024. So we used the flux ratio and magnitude, and we were able to efficiently remove the stellar sources like this. So yeah, finally but still, so based on this kind of process, we reduced the number of sources residing in this area. So we studied about 2 million sources, and finally we have 1.5 thousand sources in this area. But still, there's a possibility that bad candidates can be included here. So we actually checked the image data. So for example, it's like this. So we checked if there's something we can see in the 1.5 micron. So I think this is okay. But sometimes we can see something like this. So some sources are here, but it's brighter than the background level. So we try to exclude this kind of sources. So, and then we try to obtain some physical parameters using SAD modeling. So we have just started to obtain the CDP results, so it's quite preliminary. So we're still trying some primary tests. So this is quite preliminary. So this is an example. And so photometry at these two bands we use as data points, and then background level 1.1 and 1.5. So these are used as upper limits. So after that, we try to see the probability distribution of the photometric redshift, and sometimes we can see this kind of things and then be excluded. This is not the Lyman break galaxy, and the redshift is about 5.7. And then, yeah, this is preliminary. And then the photometric redshift is around, here, redshift 12. And then we also check the stellar masses, and the mass range is like this, between 10 to the 9 and between 10 to the 9 and 10 to the 10. And then we also try to see the star formation rate. So you can see the error bar is quite large, so we only use the 2 data points, so it's quite uncertain. And then we just try to compare with some other main sequence line from these two papers to see the kind of main sequence evolution from redshift 0 to 6. So this is the current status of this work. So this is kind of summary. We use the JWST COSMOS-Web data and try to select 1.5 dropout candidates. And through this process, we finally have 48 candidates. But we are trying to obtain more reliable physical parameters. So yes, that's it for today. Thank you very much.
Questions for Seong Jin? I also want to encourage junior members to ask questions. So maybe I can start with one. So actually, from the color selection, you have 1,500, but then with the visual inspection, you reduce to about 50.
Yes.
So what are the rest, like the 1,450 sources? What kind
100. So this kind of sources. So from 1,500 sources, we try to exclude these kind of sources.
Okay, I see.
Yeah.
Maybe still the signal to noise for the source over there is still very low, right?
Yes.
Okay.
But anyway, we can see if something is here by eye.
Okay. But and to me, it's consistent with the noise fluctuation. Maybe it's like in the peak of the noise, but
Probably,
yeah.
yeah.
Okay.
That's possible.
Okay.
But anyway, we try to exclude it if there is something in here.
Okay. Yeah, please.
Why
You can wait for it.
why have when you have photo redshift, why have 2 peak? What you excluded, but why have this kind of things?
You mean this kind of
Yes,
things?
yes.
So SIGAL provides the results in terms of the Bayesian analysis. So this is kind of a probability distribution. So this is a distribution, probability distribution. So in this case, the peak is here. So the best fit models, you can see this kind of models at redshift 5.7 here. But the other sources, it looks like this. Strong peak is around redshift 12.
Okay, one more question in the back. Please.
So could you go back to the next slide, please? in the probability distribution, the two peaks, the biggest one and then right and left to it, those two are like pretty much similar. So how do we believe that that the maximum one is the responsible for this particular curve? Like, why couldn't be the second one?
This is not similar. This is restricted to 3, 4, 5. So, and then, there's no way. So we have to accept this kind of things. But in my work, this is none of my business. Because the peak is not here. Anyway, if you want to see this kind of 5.7 sources, I think this is one sources you can take. Yes.
Okay, thank you. So,
Is this common
Sorry?
with Sigal?
Yes, this is a Seagal.
Is this common, this kind of property?
Can you repeat your question?
This kind of property, is this common with Sigal?
Yes, yes.
Yes. Thank you.
yeah, so I think we should move on. So let's thank Seong Jin again.